Well, hi there. Thanks for joining me today for an update on Climate Change 101. My name is Dr. Tom Suchanek, and I'm a marine ecologist from UC Davis. Over the past 40 years, I've been conducting research on environmental contaminants. And for the last 20 of those years, I've been educating people about climate change, caused primarily by the most critical pollutant of our time, carbon dioxide. My goal today is to help you understand three things. First, what does the science tell us about climate change? Second, why are we experiencing so many extreme weather events? And third, what can we all do to help solve this crisis? And even more importantly, what's the urgency to develop these solutions? How much time do we have left? So with that, let's begin. I've broken this presentation up into two sections. First section on the left will deal with greenhouse gases and the greenhouse effect. Next, how do these greenhouse gases affect the Earth's climate? And what are the environmental and human impacts that we're experiencing? That section is here, and it will take about 30 minutes. Next, we'll go over the amazing different kinds of solutions that we can have to solve this crisis. And the big question is, can we succeed? So let's start with the basics. This cartoon by Graham McKay is amazing. It basically epitomizes the crises that we have right now, all happening at the same time. We've got COVID, which is occurring for maybe 1 to 2 years. We've already had 500,000 deaths in the US, 2.5 million globally. And now we have different mutants or variants that are coming in. So it's unclear how long that's really going to last. Next, we have the economy, which we are in a recession right now, totally unstable situation with stock points going up and down several hundred points a day. That's pretty crazy, maybe 2 to 4 years on that. And then we have the impacts that we're experiencing from climate change now, and that will overtake all of these in magnitude to infinity if we don't deal with it immediately. Okay, so I hope I'm not trying to scare you here, but maybe a little bit, maybe a lot actually, because what we're experiencing now will be multiplied many, many times to our children, our grandchildren, and hopefully one of us will be able to take care of it. So what does the science tell us? Let's start off with the greenhouse effect. We have the natural greenhouse effect on the left and the human enhanced greenhouse effect on the right. In the natural greenhouse effect, the sun beats down on the earth heats up a little bit, and some of that heat is reflected back out into space. But because we have produced carbon dioxide, methane, and nitrous oxide, we do have a blanket of warm air, of heat trapping gases in the atmosphere that are represented by this orange layer here. It's not orange, but it's there. And if we didn't have that layer, our planet would be basically ice. So we need that, but we don't need too much of it. The human enhanced greenhouse effect is the same process. Sun beats down on the earth reflects some of that back into space. But now, because we've created and emitted so much more carbon dioxide and methane and nitrous oxide into the atmosphere, those heat trapping gases are increasing the temperature on our Earth. And the greenhouse effect basically creates global warming, which then drives climate change. That's the basis of it. So what are these greenhouse gases? What are they, and where are they coming from? Let's start with carbon dioxide. Carbon dioxide represents about 83% of our greenhouse gases, and they come from the burning of fossil fuels, coal, oil, and natural gas. And that is from gasoline engines for planes and trains and automobiles, industrial manufacturing plants, and residential heating and cooling and the lights in your house, for that matter. Next is methane. Methane comprises about 9% of our greenhouse gases. And where does it come from? It does come from cattle pooping and burping, about 95% from burping, actually. The other 5% is from the other end. And leakage from fracking operations for oil and gas drilling. There's a lot of those around right now. And from landfills and waste, from decomposition. You pile up a bunch of organic matter, and within a year, natural methane producing bacteria start to build up and release that methane out into the air. And the melting of tundra is the same thing. Once the snow melts, the peat heats up and also methane producing bacteria act there as well. So we also have the last one that we're going to consider here seriously is nitrous oxide, which comprises about 3% of our greenhouse gases in the atmosphere. That comes from agricultural soil management, like synthetic nitrogen fertilizers, animal waste fertilizers, and human wastewater treatment plants. So from now on, we're going to try to tackle in this presentation a discussion about mostly carbon dioxide. So let's go for that. What are the sources of these in Sacramento County? Well, the emissions that we have in Sacramento County for carbon dioxide are primarily from vehicles, from transportation of all kinds. And interestingly, for the US, it's only 28%, but because California has so many more cars and vehicles, that's why ours is so high. And that's one of the big things that we need to tackle in many of these climate action plans. The second biggest contributor to CO2 emissions in Sacramento County is the industrial manufacturing plants. And that's 24% of our greenhouse gases, mostly CO2. And the third next one in line is electricity, both electricity that we produce in-state and also that we import from other states along the grid. So that's 15% of our CO2. And let's take a look at how carbon dioxide has changed over time. Here's a graph with atmospheric concentrations of carbon dioxide on the left in parts per million. And the time frame is the last 1,000 years. So each one of these little dots represents a data point from ice cores. Ice cores contain bubbles of air, which are, depending on where they are in the core, could represent different timeframes back at least 1,000 years in this graph. And the concentration of CO2 in this particular figure from 1,000 years ago is bumping along at about 280 parts per million until we come up to the Industrial Revolution, 1700s or so, end of the 1700s. And that's when we started burning coal to fuel our steam engines. And from then on, carbon dioxide started ramping up quickly up to this exponential increase up to where we are now at 415 parts per million. Let's go back even further. This is a graph of the same axis over here, the concentrations of carbon dioxide in parts per million. And we're now back about 1 million years. So as the concentration of carbon dioxide goes up and down, every time it dips down, we have another ice age, about every 100,000 years. And we come forward to the present until humans appear about 200,000 years ago, and further to the present until we come to that industrial revolution again, roughly 1800. And from there, it just ramps straight up, exponentially straight up, until where we are now at 415. Well, how do fossil fuels figure into this carbon dioxide emissions? Well, fossil fuels are responsible for about 94% of total carbon dioxide emissions from human sources, and about 42% from coal, 33% from oil, and 19% from natural gas. Cement plants actually produce a fair amount of carbon dioxide as well. They take up a lot of energy, so they're burning stuff, but they also emit carbon dioxide. So sometimes they can contribute 6% on top of that. So globally, our global community has been emitting about 100 million tons of carbon dioxide each day into the Earth's atmosphere. That ramps up to about 40 billion tons per year. It's hard to conceive, even for me, how much that is, especially since it's a gas, that we can't touch it, feel it, smell it, feel it. We just can't see it. And yet, as a gas, it has a tremendous amount of mass, which is 100 million tons a day and 4 billion tons a year. That's all up in our atmosphere. It's just pretty incredible. So once all this stuff's in the atmosphere, where does it go? Where does all the CO2 go? Well, here's a bathtub. Let's pretend this bathtub is the atmosphere. And this spigot is CO2 being emitted into the atmosphere, all the carbon dioxide. Well, it does have some places where it drains out. And that drain is some of it, 25% of it, is absorbed by plants. And the Amazon rainforest actually takes up 5% of those emissions by itself. 25% is also absorbed by the oceans. And 50%, unfortunately, remains in the atmosphere. And that's the problem that we're dealing with right now. So what's that doing to our atmosphere? Well, here's our first critical graph, number one. I have three graphs in this presentation that I would like you to understand very clearly. So I'm going to walk you through this. Let me just take it one step at a time. On the left, we have the temperature increase from the beginning of the Industrial Revolution. Here's the line right here. The zero line is what it was like at the beginning of the Industrial Revolution. This is in degrees centigrade. Over on the right, we have concentration of carbon dioxide in the atmosphere. And you can see that as the carbon dioxide increases, this white line, the temperature also increases, not exactly the same way, but it does jump around, but it's also correlated with carbon dioxide. And so far, we've increased the temperature above Industrial Revolution to about 1 degree centigrade. Now that's 1.8 degree Fahrenheit. That's not a lot in conceptual terms, but in terms of an increase, especially the way it's going, it's very dangerous and very concerning to atmospheric scientists. So the last time CO2 concentrations were this high, 415 parts per million, humans didn't even exist. That's 800,000 to 20 million years ago. At that time, global temperatures were substantially higher. There was almost no ice on the planet, and sea level was about 100 foot higher. Remember, Sacramento is at 25-foot elevation. Where would your house be if this were the case? So this is critical graph number 2. It's basically the same graph that we just looked at, a little expanded. Instead of stopping at 1 degree temperature increase, we're now up at potentially 4 degrees increase. And the ordinate down here is from 2000 to the end of the century. Instead of stopping at 2020, we're now extending our projections to 2100. So what does this mean? Well, here we are. The temperature is increasing. This is what we've done so far. And bringing us up to today at 2021, we've increased about a little over 1 degree Fahrenheit, centigrade, and that's where we are now. A little bit more than 1 degree, same as the last graph. Now, if we continue on with what we call business as usual, we don't change anything, we just continue on, by 2100, we would be up to this point, which is plus 3.6 degrees centigrade, or in Fahrenheit degrees is 6.5 degrees. That's catastrophic. I'm not sure that we would be able to survive that as a civilization. Now, the Paris Climate Accord has set some goals. Scientists have been looking at this and studying this for over 40 years, and they've accumulated all their data together to make recommendations of where we should be right now trying to strive to. In order to avoid the most extreme impacts from climate change, we should limit our temperature increase above the pre-industrial levels to either 1.5 or at the most 2 degrees centigrade. And that's above this level here. So that's the basis on which we're working to solve this problem. So what are the consequences of having a much higher CO2 level in our atmosphere? And what will happen if we extend beyond 2 degrees? Well, what would happen if we reach 2 degrees? We're coming up to that pretty soon. What would happen if we were to increase 3 degrees centigrade? What about 4 degrees centigrade? Let's take a look at those scenarios and see what would happen. So with 2 degrees centigrade, we would pretty much be pretty close to our stated goal and should be very proud of ourselves for the progress we had made, although there are still some very troubling impacts that would result. The risk of river flooding would more than double, and we know that our rivers are flooding all over the US now. 90% of coral reefs would be bleached. Droughts would last 4 months longer, and over 50% of the world's population would be exposed to lethal heat for more than 20 days per year. Let's look at the consequences of a 3 degree warming. Here's 3 degrees. Now we're into totally different territory. I want to be very clear about this. 3 to 4 degrees centigrade warming future is a very bleak outcome, especially for the world's most vulnerable populations and nations of communities who experience the impacts of climate change disproportionately. We need to do better than this, way better, but let's see what the consequences would be for a 3-degree warming world. Arctic sea ice would be gone in 2 out of every 3 summers. 50% of insect species would lose more than half of their habitat range. Droughts would extend 11 months longer than they are now. And the area burned by summer wildfires in the Mediterranean would double. Now remember, Sacramento is in a Mediterranean, California is in a Mediterranean climate. So think about our fires right now and think about them doubling. That's not a good thought. Now let's see, I don't want to do this, but let's see what a 4-degree warming would do. This would be catastrophic. Sea level in this rise in this century would be up 4 feet above what it is now. More than 2/3 of the glaciers in the Himalayan mountains would be melted. 1 in 6 species would go extinct. And 3/4 of the world's population would be exposed to lethal heat for more than 20 days a year. Now, these are all projections, yes, but we could get there. That's not out of the realm of possibility. But now let's look at what's already happening in our country and on our planet. Let's look at some of these climate change impacts that are already affecting us. First, we need to just make a definition here because some people don't understand the difference between weather and climate. Weather is basically what slaps you in the face as you walk out of your house. Climate is an average of the weather over specific periods of time, like months or years or decades or centuries. So that's the difference between weather and climate. Weather is at your house, climate is over a long period of time. So let's look at some of the things that are happening now. And I'm going to show you a list of things here, but then I'm going to give you some examples after that. We're experiencing extreme temperature fluctuations. And that's both hot and cold. And we'll take a look at those. We're experiencing extreme droughts. We'll look at those. Extreme fires and dangerous air quality. With droughts comes dryness. And then when everything is dried out, it lights a fuse for everything else. The fires can be happening from campfires getting loose or a cigarette out the car window or a backfire or anything really, because set it off. And then we have dangerous air quality as we've seen recently with that. We also have extreme weather events like storms, winds, hurricanes, tornadoes, floods. And we have extreme snowpack fluctuations with events called whiplash events, where one year we'll have almost no snow in the Sierra Nevada. The next year we have like 200% of normal. And then we have the polar vortex. We'll go over that a little bit as well. We have rapid sea level rise. We are now melting 1.2 trillion tons of ice each year. That goes into the ocean, raises it up. I've already told you how bad it can get, but that could back up to the Sacramento River and affect downtown. We have increasing extinction events. Right now, we're losing over 200 species a day, going extinct forever. And that affects not only the songbirds in your backyard, but also the pollinators that California agriculture is so dependent on for fruits and nuts and vegetables. And finally, they're increasing, climate change is increasing human health risks and mortality. And we'll talk a little bit about that as well. What we're experiencing is extreme and unpredictable events. And this is happening daily. It's not just in the future like we've been talking about in the past to the year 2100. This is happening every day. And if you look on your news broadcasts, you can see that somewhere in the country, we're having extreme weather events. And unfortunately, that's disadvantaged communities are being affected disproportionately as well. So let's talk about some of these impacts in more detail. Extreme cold in the lower 48. This is caused by a polar vortex. On the left, we have the jet stream, the polar jet stream circling the North Pole area, and it's counterclockwise. And this is where we have all the low pressure systems and cold air. Here's the lower 48 states right here. Now, when we have a polar vortex, because the heat budget of the Earth has been disrupted, we now get high pressure systems disrupting the flow of the jet stream. It pushes up against the jet stream, and that pushes down the polar vortex down into the lower 48. That is what a polar vortex is. It can happen in the winter, which we just had in Texas. It can happen in the middle of the summer, but this is what happens. The cold air comes down into the lower 48. Now let's go to the other end of the heat spectrum and go to the extreme temperatures and droughts. This is the Palmer Hydrological Drought Index during a drought from 2012 to 2017. The darker the color, the more intense the drought. And you can see the West has much more drought experience than the rest of the country. Let's take a closer look at California. Here's California, and the Hydrological Drought Index has several categories: abnormally dry, moderate dry, severe drought, extreme drought, and then this last one that I've outlined here is exceptional drought. Now, before this drought here, we didn't have an exceptional drought category. They had to create a new color and a new category to describe the intensity of this drought. That's just unbelievable. We're doing this with many things. It's like taking a foot-long ruler and expanding it to a yard long to describe what the intensity is and extent of some of these changes that we're experiencing, which are getting worse and worse and worse. Once we have this drought situation, like I mentioned, it can fuse fires. And here we have a number of fires across the West that are greater than 1,000 acres on U.S. Forest Service land. Here's the number of fires on the left and time on the bottom, starting in the 1970s, going up to about 2015 or 16. And each one of those bars represent a separate year and how many fires we had in that year. Now, back in the 1970s, we didn't have much going on. Well, we had 40 or 50 fires. But as we move forward, every once in a while, we're getting higher and higher. And this is an average. This orange line is an average through all of those years and paints a picture of where we're going, just like an exponential curve is rising. So what happens to the air quality in these? First of all, it also affects the fire season. And right now, the fire season has expanded by 75 days across the Sierra Nevada. Some of it's earlier and some of it's later, but we have now 75 days more fire season than we had in the past. So now what happens with the air quality? This is a figure that has air quality index. Index goes from 0 to 500, and these are the ones that we're experiencing in Sacramento County. Here's a map of Sacramento County, and you can take this map and just plant it right over here. This is basically the same area. Here's Sacramento in the middle. And let's look at the colors, which represent different levels of air quality index. The red in all this area, and this is from September of last year. We had weeks and weeks of this happening with the fires. This is unhealthy air, the red. In the purple, we have very, very unhealthy air. And in this brown area, we have hazardous area. And we were all told to do not go out and bike and exercise, stay inside when you can, get air filters if you can. This is what's happened. And we are, and if you were in Sacramento in the last couple of years, you've been experiencing this yourself. And actually, it's not just smoke from fires, from forest fires that's affecting us. It's also some other studies. Now, scientists from Harvard University have just come out with a study that indicates air pollution from the burning of fossil fuels alone, just fossil fuels. All of our planes, trains, and automobiles was responsible for more than 8 million deaths worldwide in 2018. That's 18% of total global mortality. That's just hard to conceive. That's just from the burning of fossil fuels. And that's primarily coming from tiny particulate matter, what's called PM 2.5. And that's 2.5 microns, which is minuscule. And that's collecting in people's lungs and giving them respiratory illness and many times ultimately death combined with other illnesses. Let's look at the other end of the spectrum here, from burning to storms and flooding, which creates a huge amount of water moving through our system. Houston had 3 500-year storms in 3 years, 2015, 16, and 17. That's 3 500-year storms. That doesn't compute. And in 2016, the US had 5 1,000-year storm floods in Texas, West Virginia, Maryland, Louisiana, and South Carolina. Again, these are 1,000-year floods in 1 year. And in May 2019, the Arkansas, Missouri, and Mississippi rivers had their worst flooding in over a century. This is getting worse and worse and faster worse. Let's take a look at the cumulative impacts of these and other types of extreme events. So here we have a map of the US with these bubbles on it. Don't read the outside stuff. I'm going to walk you through this. Each one of these bubbles represents an event that was over $1 billion in damage. This was from 2018, and there were 14 of these events. I'm just going to read through what these events were. This is fires. We had droughts. We had hailstorms, tornadoes, hurricanes, freezing events, lightning strikes. All of these were totaling $93 billion worth of damage in 2018. Now, over the last 40 years, these $1 billion damages have gotten worse and worse and worse. And this figure shows you the number of the billion-dollar events on the left side, which means every single one of these bars totals the amount of the number of billion-dollar events over time. And you can see that down here, 1980 to 2020. In the 1980s, there wasn't much going on in terms of billion-dollar events, maybe 4 or 5, that's enough. But then over time, as we came towards the future, those got bigger and bigger. Those graphs lines got bigger and bigger. And now we're up to like $16 billion events. And in terms of cost, there's a red line here that you may or may not be able to see, but the red line represents the cost of these events. We all know that each one of them was over $1 billion. But let's give you some examples. Here's this one here in 2011 was 125 billion. This one in 2005 is 225 billion. And this one up here is 322 billion, getting higher and higher overall in the long run. And sometimes people say, this is going to cost too much to deal with this climate change. We just can't afford that. Well, the cost of waiting would be tremendously worse. It would be hundreds to thousands of times worse because we're going to be dealing with tremendously increasing impacts from climate change. I'm just going to show you one more here on this graph. This is the Texas freeze that just occurred as I was preparing this presentation. It's caused by a polar vortex, because we know what that is, in February 2021. That one event was over $100 billion and over 70 deaths, and they keep accumulating now as I'm preparing this presentation. So 100 billion just for one event, and think about all these others. So we're getting higher and higher, faster and faster. So we need to find solutions to this crisis before it overwhelms us. So we've covered now the greenhouse gases, climate change, and the impacts that we're experiencing. So the second part of this presentation is, what are the solutions that we have to solve this problem? Well, we have some pretty interesting and very promising solutions coming on board. Technological solutions, legislative and political solutions, and market-based solutions. So let's start with some alternatives to fossil fuels first. Question is, can we solve this crisis soon enough before we come on to just massive extreme impacts? Okay. Alternative energy sources, solar. This is an endless renewable energy source, right? Well, maybe not quite. We only have 4.5 billion years to go until our sun gives away. So I guess we've got a little bit of leeway with that. We can still be using the sun and depending on it for a while, hopefully. And in California, we rely on 20% from solar sources. The USA, only 2%. So the rest of the country has a ways to go to catch up with California in terms of its solar component. We have photovoltaic cells, and this is typical of the way they're installed on houses now. But now they're creating photovoltaic cells that are embedded into roof tiles and into siding. Tesla is doing this mostly. And now we can collect energy, sun's energy, from all parts of our house. So that's a tremendous advancement that's coming up on board. The cost of photovoltaics has come down tremendously. In the 1970s till now, it's gone down 99%, and it's still going down now. So this is a very economical way to go in terms of getting alternative energy, renewable energy. But there's another form of solar energy that we have. It's called solar power towers or heliostats. So here's a configuration here. All these white dots. Now you may have heard of this before, but each one of these white dots is a mirror that's pointing up towards this tower here. And each one reflects sunlight from the mirror up to the top, where we have molten salts, and they have a high heat capacity. So they heat up the molten salts and they retain their energy and their heat long past the time the sun is shining. So we can use this stored energy to then drive the turbines to produce electricity, even when the sun's not shining. And there are many places around the world, including the Mojave Desert in the US, where we have these solar power towers and heliostats. So we're making progress on that. Another form of renewable energy is wind. Over 5% of the world's energy supply comes from wind, and 7.5% of our energy comes from wind in California. Now, here's a couple of examples of wind farms, wind turbine farms, one in Palm Springs and the other one just down in the Bay Area at Altamont Pass, which you probably have seen. This one, Altamont Pass, is one of the oldest, and at one time, the largest wind turbine farm in the world. And people have been concerned about the turbines killing birds, the blades. So scientists have been working on this, and they've tried to mess around with the blades and configurations and sizes and configurations of those. Haven't been too successful with that. However, they have now settled onto a scheme where they actually paint part of the blades. And luckily, this reduces bird deaths by 72%. So we're gaining on saving the environment while we're saving the environment. So that's great news. So wind power actually is not only land-based, it's ocean-based as well. So this is in the North Sea, just outside of London. And there's tremendous wind turbine farms all over the North Sea, many more proposed, many more being built right now. Huge amount that's supplying energy for Northern Europe and Great Britain. And lo and behold, here's a map of California wind speed. And the darker the color, the higher the wind. And way up north, we've got the highest winds off the coast of California. And right now they are doing prototypes of wind-powered turbines in that area to see if we can utilize some of that wind, turn it into energy, and feed it into the grid so that all the rest of us can use it as well. So besides solar and wind, there's many other potential sources of renewable energy. So we've covered solar, we've covered the wind, we already have hydro in California, and we also have geothermal up in Lake County where it's possible, where the geothermal fields are. But we also have potential tidal energy, ocean thermal energy conversion. The difference is temperature between the top and the bottom of the water column. We have wave energy. We have current energy. All of these are in prototype mode, and we're trying to perfect them to add to our caveat of things that can help us produce energy that are not fossil fuels. So once we collect all the energy from all of these sources that are usable, what do we do with all that electricity? How can we store it? Well, to the rescue, Elon Musk comes again. We are now developing regional, or what we call grid scale, battery storage facilities. Elon Musk was the first person, or the first company in Tesla to develop one of these. This is an example, a big, huge photovoltaic field producing energy going into this huge Tesla storage facility that can be used later on. Now, Tesla has also come out with a new form of battery that's supposed to be 20% more efficient. Just did that this last year. They won't be implemented for a while now, but technology is increasing all the time. And this particular one was the first and the largest battery storage project in the world. And there's over a dozen companies worldwide that are now developing mass battery storage facilities. So where should we start to reduce our emissions that are going into the atmosphere? Well, we should start with transportation, probably, because 40% of California carbon emissions are coming from transportation. And for the country, 28%, as I mentioned before, are coming from transportation. So let's focus on transportation for a minute in terms of getting rid of our carbon dioxide in the atmosphere. Starting off, Governor Newsom signed an executive order last September that halts the sales of all new gasoline cars and trucks in California by the year 2035. That's great news. And on January 25th, President Biden promised to convert the entire federal fleet to electric vehicles. Hallelujah. That's going to make a huge difference. And 3 days later, General Motors decided that they will only sell zero emissions vehicles by 2035. Amazing progress. This is just incredible. This is happening faster and faster. And now over a dozen countries have committed to banning new gasoline automobiles over the next 1 to 2 decades. This is growing. The movement is growing to get off of fossil fuels tremendously. And it's not just automobiles. Here we have electric semis. Again, Tesla produced the first electric semi, all electric semi by November 17. And Elon Musk, this cab goes 0 to 60 in 5 seconds. I wouldn't want to go in there. U.S. military has known what's happening for decades, and they are converting to all electric or hybrid electrics for their Jeeps, their transport vehicles, and their tanks for that matter. And the ultimate, electric airplanes. Harbor Air has become the first electric airline in December of 2019 in these little planes. They've got to start somewhere. And these guys fly fishermen and hunters to the backcountry and back. That's in Vancouver, British Columbia. They're making it. And Airbus has a competition out now to compete for who can build or engineer the most efficient airplane engine. And we project now that within 20 years, we're likely to have commercial airplanes carrying over 100 passengers. Imagine that. Just phenomenal. Now, one of the most important steps in solving the climate crisis is the US-led Paris Climate Accord. President Obama in 2015 pulled together 196 countries to ratify in 2016 the Paris Climate Agreement or Paris Climate Accord. And remember, the Paris Climate Accord is what has given us direction to keep our temperature, the global temperature, below 1.5 to 2 degrees above the pre-industrial level. So they're making tremendous progress on that. However, in 2017, we were pulled out of the Paris Accord. And for the last 4 years, we've been out of that agreement. However, as of the new Biden administration, as of January, we're back in. And President Biden signed several executive orders now focusing on climate change, which has become a central priority of the Biden administration. And some more good news, we have nearly 1,500 governments worldwide, states and countries, that have now declared climate emergencies, which allow them to pass legislation to appropriate money to solve some of these problems. That's great news. And over 6,000 companies in 7,000 cities in 133 countries are following the Paris Agreement protocols. So great news all around there, but we need to do more. Let's get down to some nuts and bolts of some other exciting solutions that we have available to us. This one is political and legislative solutions. And carbon pricing is one of those. And this will discourage consumers from buying or using fossil fuel vehicles by putting a price on carbon. And typically, it would be like $10 or $15 per ton of carbon emitted, which is equivalent to about 3 barrels of oil. And that would increase over time, each year, some percentage. And over time, that would get more and more and more expensive to use carbon-based fuels like fossil fuels, and would preferentially provide incentives for non-fossil fuels. Now, each one of these countries with a different color either has a carbon pricing structure to it or is anticipating it and intending to put in carbon pricing. Notice that the United States does not have any color nationally, although some states and cities are. Hopefully, we will be able to pass legislation in this next Congress to allow us to have some kind of carbon pricing established. So there's one more important approach to changing our energy habits and policies, and that is market-based solutions through divestments away from fossil fuels and investments into renewables. Now, there's a company called BlackRock about a year ago, which is the largest asset manager in the world at $6.9 trillion in assets. BlackRock is the world's biggest owner of fossil fuel companies. Imagine that. And they have decided that they're now putting climate change and sustainability at the core of their investment strategy. Holy cow. A fossil fuel owner of assets is doing this. Amazing. And now they're moving investments away from coal. Incredible. And they're ramping up pressure on polluters. Even more fantastic. And European Investment Bank, which is the largest public bank in the world, will stop lending money for fossil fuel projects. Wow. And they've already allocated 8 billion euros to reduce carbon pollution. And they've committed 1 trillion euros over the next decade to combat climate change. These are all fantastic improvements and will allow us to ramp up quickly. So what's the bottom line of all this? Well, here's critical graph number 3. You've seen most of this already. Again, on the side, this is carbon dioxide emissions into the atmosphere, 40 billion tons a year. And over here, we've expanded the axis from 1980 to the end of the century, 2100. So here we go. This is black line is the amount of carbon dioxide we keep putting into the atmosphere. And each one of these little lines is a model run projecting how much we have to decrease that over time to get down to where we need to be is zero emissions. So I'm going to walk you through this. So back here in 1980, we were emitting carbon dioxide into the atmosphere till the year 2000. If we stopped at that point and started reducing our carbon dioxide, we would have only had to reduce it by 2% per year. And obviously we didn't do that. Carbon dioxide into the atmosphere was still going up and up. We're here now in 2021. And if we start now, we basically have to reduce our carbon dioxide emissions by 5% per year. That's a lot tougher, but we could do it. If we don't do anything for 10 years, these 10 dots represent years. If we waited till the year 2030, we will have to start lowering our emissions by 9% per year. That's a huge challenge to get all the countries of the world trying to do that. So what we need to do is lower this curve, slow the curve, and stop the spread of carbon dioxide. Same thing for COVID. Lower the curve, bend the curve, and stop the spread. That's what we need to do with carbon dioxide. It's all up to you. It's all up to me. Will we be able to lower emissions fast enough? I'm not sure. But to accomplish this, we need to use all the tools in our toolbox. These tools and all the tools we just talked about. We are already making great progress, but we need to do more. We need to do it faster, and we need to do it now. And if we could put a man on the moon in 1969 with only the computing power that we now have in one single iPhone, and we were able to put a rover on Mars this year, which was 130 million miles away, and have it do all those chores, we can certainly solve climate change. No question about it. The question is, do we have the political will to do that? The most critical actions you can take are: 1, educate. Educate yourself, your kids, your friends, and your tribe, those peeps who you hang out with. 2, communicate with your elected officials. That includes your federal representatives and senators, your state officials, and your county supervisors and city council members, especially if they're working on developing climate action plans like they are now. I know that doesn't sound like something you would typically do, but trust me, it's really powerful. These elected officials believe that every communication they receive, whether it's a tweet, a phone call, a postcard, an email, anything, represents 100 to 1,000 times more communications from other people who would never think of communicating with them. So that is powerful. If that's something you consider, contact me. I'll be able to help you out. And of course, the most important thing of all is to vote in all local, state, and national elections for those individuals who will work hard to solve this crisis. The bottom line is, right back where we started, climate change will overwhelm us if we don't do it now. Take care of it. Time is running out. Thanks for listening.